Hi, this is Dr. C. Lakshmipati, Associate Professor, Department of H&S, SRIT, Engineering College, Anandapur. So today we are discussing about Unit 1, Wave Optics. So physical optics. What is the physical optics? Optics is a branch of physics that deals with the study of light and its properties. So optics is geometrical optics, rectilinear propagation of light, reflection, refraction, physical optics, wave nature of light, interference, diffraction, polarization, quantum optics, particle nature of light, Compton effect, photoelectric effect, etc. So the main object of physical optics is explain optical phenomena that arise from the wave-like nature of the light. So wave nature of light, unlike geometrical optics which treats light as rays, physical optics treats light as a wave. Interference this occurs when two or more waves meet and combine, resulting in increased or decreased amplitude. Diffraction, the bending of light waves as they pass around obstacle or through openings, a phenomenon essential for understanding how light interacts with the small objects. Next, polarization. This refers to the orientation of light waves, oscillations, and is another wave specific phenomenon explained by physical optics. Wave propagation, it provides a framework to understand the transport of light by wave propagation using concepts like Maxwell equations. Okay, what is the interference? When two or more waves superpositions on another, then at the point of superposition, there will be change in intensity. This is known as interference based on superposition or path difference between the waves. Interference is two types, which is constructive interference and destructive interference. So constructive interference, when first of one of the wave fall on the crest of the another wave, or when thought falls on the through, then at a point of superposition the intensity will be maximum and is called the constructive interference. Next, destructive interference, when crest of one wave falls on the through of another wave, or when the trough falls on the crust, then at a point of superposition the intensity will be minimum and is called constructive interference. Okay, so the diagram shown in the figure. Next, conditions for the interference. So when waves come together, they can interfere consequently or destructively to set up a stable and clear interference pattern. Two conditions must be met. One, the sources of the waves must be coherent, which means they emit identical waves with a constant phase difference. The waves should be monochromatic. They should of a single be a single of wavelength. Next, let us say we have two sources sending out identical waves in phase. Whether the constructive or destructive interference occurs at a point near the source depends on the path length differences delta, which the distance from the point to one source minus the distance from the point to the other sources. Another condition for constructive interference, delta equal to m lambda, where m is the integer. Condition for the destructive interference, delta equal to m plus half into lambda. So the first person to observe the interference of light was Thomson Young in 1801. So he used sunlight passing through two closely spaced slits. It was a difficult experiment since his source was not even close to being monochromatic. So, but Young's double slit experiment provided the first indip- indisputable evidence of light acting as a wave. Okay, note that you cannot use through light sources. Suppose two light bulbs, two candles, etc. Because they each experiments random changes in phase about once every 10 power minus 8 seconds. Okay, interference condition for thin films or interference in thin film by reflection. Okay, so here we have what is that the optical path difference, the intensity of the interference pattern depending on the optical path difference, that is path difference tau equal to n into AB plus BC minus AD. Here AB, BC, AD are the calculated by the diagram according to diagram. Then the destructive interference we get what is that 2 nd cos beta equal to m lambda. Then the constructive interference condition is 2 nd cos beta into n m minus half into lambda. So next, Newton rings, formation of Newton rings. The arrangement is shown in figure. So in the arrangement containing what is that traveling microscope and inclined glass plate and plano convex lens and plain glass plate. Okay, so in this setup, mainly we have what is that plano convex lens and plain glass plate. So which the lens having one side will be flattened, another side will be curved. Then the lens is known as plano convex lens. The curved surface is placed on the plain glass plate. In between two occurs air layer. This air layer acts as a thin film. Okay, so after interference, we get the a pattern, interference pattern in the form of rings. So shown in the figure. So condition for bright ring is 2 meter equal to n plus half into lambda. Condition for the dark ring is 2 meter equal to n lambda. Next we have to go. So applications of interference. Interference is used to determine the wavelength of light. It is used to find the difference in wavelengths of two spectral lines having small separation. Find the thickness of the transparent materials. So determine the diffractive index of the transparent solids, liquids and gases. To find the velocity of light, next to test the optical flatness of surfaces, to find the reflecting power of the lens and prism surfaces. Okay, next we have to going. Next subunit is diffraction. Okay, diffraction is the bending as the bending of light around the corners of the obstacle or aperture into the origin of geometrical shadow to the obstacle. Next, so diffraction differences between the interference and diffraction. So there will be some changes are there. So it is interference. It is due to the superposition of two waves organized from the originated from the two different coherent sources. But diffraction is the it is due to the superposition of secondary wavelets originated from the same source. So interference, the bandwidth is equal. In the diffraction, bandwidth is decreases as the order increases. So in the interference, all the bright fringes will be same intensity. So in the diffraction, the intensity of the bright fringes varies with the diffraction pattern. So the diagram is also shown in figure. Okay. Next, we have what is the Fraunhofer diffraction at single slit or due to single slit. So it is the evidence of the wave nature of light. Okay. In the Fraunhofer diffraction, the source and the screen are in a infinite distance from the obstacle. Okay. And the wavelength is plane. So let us particle beam and the arrangement of the Fraunhofer diffraction due to synchronicity is shown in figure. Okay. Then here the path differences we get. What is that? 2 pi by lambda into sine theta. Okay, then we get what is that 2 pi by lambda into, therefore the phase difference is 2 pi by lambda into path difference. That is 2 pi by lambda into e sine theta. Then we get what is that amplitude a equal to a n a sine n pi by lambda into sine pi by lambda. Okay, next we have to, then there will be some conditions in the Fraunhofer diffraction due to single slit. So the conditions will be shown in the topic. Then we get the graph according to diffraction pattern. It is there will be some at the center point we get what is that maximum intensity. That means it is zero order or principal maxima. Either side of the principal maxima we get secondary maximas. In between that we get the minimum intensity of the pattern, diffraction pattern as shown in the figure. Next we have what is that Fraunhofer diffraction due to double slit. So let us a parallel beam of monochromatic light of wavelength lambda be incident normally up to the parallel slits AB and CD. Each of the B is there separated by d distance. The distance between the corresponding points of two slits will be B plus D. So the arrangement of the Fraunhofer diffraction due to single slit is shown figure. Then here also as related to the single slit. Then we get the conditions after the diffraction. We get so finally we get what is the conditions similar to the single slit. Next we have what is that diffraction grating. An arrangement of consisting of large number of parallel slits of the same width and separated by equal opaque spaces is called diffraction grating. In optics, a diffraction grating is an optical grating with a periodic structure that diffracts light or another type of electromagnetic radiation into several beams traveling in different directions. So the diffraction grating is shown in figure. So next we have applications of diffraction. The wavelength of spectral lines can be measured by using diffraction grating. The wavelength of X-rays can be determined by X-ray diffraction. The structures of the crystal can be determined by the X-ray diffraction. The velocity of the sound in liquids can be determined by using the ultrasonic diffractions. So the size and shape of the tumors, ulcers, etc. inside the human body can be assigned by the ultrasound scanning. Okay, so next we have what is that introduction to the polarization. So next subunit is polarization. Then the introduction is polarization in the constant of waves like light refers to the restriction of wave oscillations to a specific direction related to the wave's propagation. There are three primary types of polarizations are there for electromagnetic waves: linear, circular and elliptical. So there are linear polarization first one. In linear polarization, the electric field of the wave oscillations along a single line confined to a plane. This plane is often referred to the plane polarization. Next, circular polarization. So the circular polarization occurs when the two linear compounds of waves are perpendicular to each other and have equal amplitudes with a 90 degrees phase difference. The electrical field vector traces out a circular path as then it is called circular polarization. Next, elliptical polarization is similar to circular polarization, but the amplitude of the two perpendicular linear compounds are not equal or the phase difference is not exactly 90 degrees. So this result in the phenomena is called elliptical polarization. Next, double reflection. So double reflection means double refraction or birefringence is an optical property where a single ray of unpolarized light emerging certain materials split into two rays. The rays that travel in different directions. This occurs because of the material has different refractive indices for different light polarization directions. In an amorphous materials, N is the same for all polarization in some crystals materials. N depends on the direction of polarization by refringes materials. Ordinary and extraordinary indicates of refractions. So there are two types of rays that is extraordinary ray and ordinary rays. So then the light passing through a circular crystal is split into two rays. Okay, this process first proposed by the Emerson Bartholinius in 1696. Okay, so it is called double refraction. Okay, so next we have what is that? Nichols prism. So nickel prism is an optical device that produces plain polarization from the unpolarized light. So it was invented by William Nichols in 1828. Okay. So then the principle is double refraction. Construction is the one of the most common forms of the nickel prism, made up of taking a calcite crystal, which is a double refraction crystal with its length 3 times of breadth. Next, it is cut into the two half along the diagonals so that their faces angles are 72 degrees and 180 degrees. So the two halves are joined together by a layer of Canada balsam, a transparent cement. It is a gum type material. A ray of unpolarized light from a monochromatic source such as sodium vapor lamp is incident on a face AC of the nickel prism. Double refraction takes place and the ray is be split into ordinary and external rays. They travel with different velocities. The refractive index of the crystal for an ordinary ray is 1.658 and for the external ray 1.486 and the refractive index of Canada balsam is 1.523. So Canada balsam does not polarize light. Okay, so then the ordinary ray is total internal reflection at the velocity of Canada balsam is prevent from the emerging from the other faces. Okay, then the reflected ordinary ray will be observed by the sides. Okay, then the nickel prism is act as a polarizer or analyzer as shown in the figure. Okay, so next we have what is that applications polarization of light. The primary application of a nickel prism is to produce plain polarized light from the unpolarized light by eliminating the ordinary ray through total internal reflections. Okay. Next, stress analysis, microscope analysis. Okay. Polarimeter and synthetic research and optical instruments. We are using these areas. So next we have what is that? Quarter wave plate. So if the thickness of the crystal plate is such that the introduce the phase difference between the ordinary ray and the external ray will be lambda by 4 or phase difference will be pi by 2, then the quarter wave plate is then the plate is known as quarter wave plate. Okay, next the quarter wave plate of the thickness is T equal to lambda by 4 into mu minus mu naught. Application, it is used to produce circularly polarized light of the optical axis of the crystal makes at an angle 45 degrees with the incident beam of light. Next, it is used to produce electrically polarized light if the optic axis of the crystal makes at an angle of the 45 degrees with the incident beam of light. Next, we have what is that half wave plate. Then the path difference between the ordinary ray and the extraordinary ray will be lambda by 2 or phase difference will be lambda by 4 or pi by 4. Then it is known as half wave plate. Okay, so then the thickness of the half wave plate is lambda by 2 into mu e minus mu naught. Application, it is produces a phase difference of pi between ordinary and extraordinary rays. Next, the emergence of a half wave plate is a plane polarized light. It rotates the azimuth of a beam of a plane polarized light by 90 degrees, provided the incident light makes at an angle 45 degrees with the optic axis of the half wave plate. Next we have, thank you, one and all.